So part 3, creating constraints. Talk about a few things here. First, we're going to talk about units of measure. Then we're going to talk about accessible HTML, then the never type, and finally, type parameter design. Okay, so this right here is the Mars Climate Orbiter. I should say the ill-fated Mars Climate Orbiter. A bad thing happened to this because there were 2 different teams of programmers working on it, and one of the teams put some of their units in imperial units like inches and centimeters, inches and feet and stuff, and the others used the SI units of centimeters and millimeters and so forth, and they got their units mixed up, and so their calculations when they sort of put them together didn't end up giving it the right numbers, and so it crashed. So that's a bummer, and it would have been nice if we could have averted that disaster by having some way to prevent ourselves from mixing up our units of measure. So here's a way we can do that using Elm. Let's start by defining a type called length, and length has a type parameter called units, or a type variable called units, and all it holds inside is 2 things. One is it holds onto a float, which is going to be the actual measurement itself, and then it's holding onto another value for the units. Now let's separately define a type for centimeters and a type for inches. And just like we had in the previous example with preview, we're going to have these just defined with a single variant that doesn't hold on to anything. So these are essentially just placeholders. They're just there to describe the units themselves. They don't actually hold any information themselves. So then we can write a function that's called centimeters, which is just sort of a convenience that takes a float and gives you back a length of centimeters. Same thing with inches. The implementations of those would just be to take the float, put it inside this length variant, and then hard code centimeters in this case and inches in the other case for the units value. We could also write a function called add, which we won't get into the implementation just yet, but it would have this type. It would say length units to length units to length units. And so if you gave it some different things that had the same units, they would work out. So I could say like add 5 centimeters and 12 centimeters, and that would work out and give me some answer that had a length centimeters, which is what I want. But if I could also do the same thing with inches, say add inches 5, inches 12, and that would work out. But if I tried to do centimeters for one and inches for the other, those would not unify, and it would give me a compile error. Okay, so here's one way we can implement add. We could say add and then immediately destructure this one variant with num1, which would be the float of the first one, and then num2 for the float of the second one. And we could also have units1 and units2, which we know from the type are going to be the same thing. So we could return length and just, by chance, we decide to pick units1 there. But we could have picked either one. We could have also said it returns units2. Another way we could do this is with what's known as a phantom type. Now that transition was pretty quick, so let me just go back and forth so you can see the two. So this is the phantom type, and this is without. Phantom type, without. So the difference is phantom type version, we still have units up here in the type of length, but we don't actually have it in the variant. We don't use it. It just sits up there being a constraint, being all constrainty, but it doesn't actually exist anywhere in the implementation. It's something that we're defining at the type level purely for the benefit of opting into a constraint that we're going to enforce by other means than what's actually inside there. So again, going back and forth. So this version actually holds on to some units. This version doesn't. This version has to pattern match on those. It has to pull the units out, and this one pulls it out in both places, whereas the other one doesn't. And then, of course, the first one ends up needing to provide that to the variant so that we can actually construct one of these length values, which it does, and it arbitrarily chooses units1, but it could just as easily have chosen units2. Whereas this one doesn't provide that at all. So this sort of begs the question, okay, well in this version we can see that it needs to be at least returning some sort of units here, either units1 or units2. But this one doesn't need to be doing that. So when it says that it takes length units and returns length units, like why is that true? I mean, is that just some sort of made up nonsense? Like really couldn't we just as easily write this one where it claims to take A, B, and return C? Yeah, we could. So in actuality, there is no constraint on length, like innate to the way that we've designed this implementation. The whole point of a phantom type is that it's a constraint that is sort of free-floating, does not exist by default, doesn't do anything by default, but when you write type annotations in Elm, you have the choice of choosing to make them more constrained than they have to be if you want to. And the compiler will respect that. So most of the time in Elm, when you write a type annotation, it's just for documentation. And you're going to put down pretty close to exactly what the compiler would infer. However, there are some examples like this where it might make sense for you to say, you know what? I know that technically I could have length of one thing and length of another thing as the two arguments, and return a length of a third thing. And I don't really care what they are. It doesn't really matter. I'm just going to ignore them anyway. So whatever. Just give me anything. Give me centimeters, millimeters, feet, users. I don't care. It doesn't matter because I'm not going to use those values anyway. You could do that, but then you'd be defeating the entire purpose of this design, which is that the whole point here is that we want them to be constrained. We want to enforce that they're the same in all three cases, or rather in the case of the two arguments. Because otherwise, it's entirely possible that you will give centimeters on one side and inches on the other side, and they'll still compile. They just will result in an unfortunately crashed Mars probe. So the trade-off here is that here we have a little bit more enforcement. Worth noting, though, that although we have a little bit more enforcement, we still have to constrain this add type annotation artificially. So notice that we chose arbitrarily to return units 1 here. Because of that, really, in actuality, we could change the length of this other one to say length units, and then length units 2, or length b, or length x, and then return length units. Really, we are still artificially constraining this one on purpose and opting into saying, actually, no, I promise that second one needs to be there. And this is sort of a natural consequence of having types that we don't really end up using in our actual calculations or anything like that. So this implementation at least requires that the return value is going to be one of the two that we gave it, but it's still not sort of innately as constrained as we've made it here. In either implementation, the phantom type or the non-phantom type version, we have to sort of opt into constraining this more if we want it to actually do its job of preventing the type mismatch between the the imperial units and the SI units. Okay, so keeping all that in mind, what are the trade-offs between the two? Like, why would I choose one or the other? I mean, I think the value of having some sort of enforcement is pretty clear. We can prevent ourselves from making the thing crash due to mixed up units of measure. However, it's, I think, less clear innately what the trade-offs are, why you might choose to use the phantom type versus actually holding on to the units inside the value. And essentially, the trade-off really comes down to the degree of flexibility that the phantom types give you, and also there's a little bit of a performance aspect to it. So in Elm, when you have a custom type with a single variant, and that variant holds on to one value, that's sort of a trivial type. Like, you look at this and you say, yeah, this is just a wrapper around this one type. Do we really need that wrapper at runtime? And the answer is no, we don't. And so actually, when Elm encounters this specific situation, a custom type with one variant that holds on to one value, it does what's called unboxing when you run it with -- optimize, which is to say, this code right here at compile time is a custom type, but at runtime it's just a float. Like, it's as if we just said type alias length equals float at runtime. Now, at compile time, it behaves exactly like a fully boxed, wrapped up custom type with all the trimmings. But at compile time, that's a performance optimization Elm's able to do because it says, well, I'll just substitute it in there. And we already checked to make sure that it's going to be used consistently across the code base. So it's fine to just unbox it and not bother putting that wrapper around it, since the wrapper was only for the benefit of the compiler anyway. However, it can't do that with this version, because this version it's holding on to two things. If it were to substitute in a float, then this other piece of information, which theoretically we might be using at runtime, would get discarded, would no longer be, it wouldn't work anymore. Now, as it happens, we know that we're not using this thing at runtime, but the compiler doesn't really have any way of guaranteeing that ahead of time. I guess theoretically it might be able to figure it out someday, but there's the running joke. With a sufficiently smart compiler, you can do just about anything. But of course, compilers don't just build themselves. So there is a definite performance advantage here, and the flexibility is both a pro and a con. On the one hand, the flexibility to be able to write essentially whatever type variables you want in here, to make them as constrained or as unconstrained as you like, is sort of a blessing and a curse. On the one hand, it's a blessing in the sense that, yeah, you can be as flexible as you want. Maybe we want this. On the other hand, it's in some sense a foot gun. I can very easily shoot myself in the foot with this and make it so that I have defined a type for add, which completely defeats the entire purpose of my going down this road anyway, and makes it so that it's perfectly possible to mix these units up and I won't get any compile time errors. So that flexibility is both a pro and a con. So essentially, the trade-off between these two options here is the phantom type version, where we only hold on to a float and we do not hold on to the units. We only have the units as part of the type variable so that we can constrain it if we want to. Gives us more performance, but fewer guarantees. It's a little bit easier to shoot ourselves in the foot. The other version doesn't quite have as good performance, but it does have a little bit more in the way of guarantees, because this is actually part of the implementation. Having said that, the performance difference here is probably not going to really matter in practice for almost all use cases. So I would definitely benchmark before worrying about this from a performance perspective.